Now I want to dive right back into integration, but I gotta use a little bit of notation first. This notation is called summation notation. This big capital sigma here is denoted for sum, and it reads the sum from 1 up to n, the sum from the bottom thing up to the n thing, of whatever it is. In this case, I've given a generic symbol xi. And the way this works is, it's x1 plus x2 plus x3 plus x4 plus x5, so on until you hit whatever the top is. So x1 all the way down to xn. As in, summation notation is just a shorthand. For example, if n is 100, I don't want to write out 100 terms, so I can use this summation notation to make it look a little bit simpler. I can also give a specific formula for what the xi was. Here's a really simple one. I can say the sum from 1 to n, but where my xi is just xi equals to I. In that case, if I plug in I equal to 1, I'm gonna get 1. If I plug in I equal to 2, I get 2. I equal to 3, I get 3. So it's 1 plus 2 plus 3, all the way down to n. Now, I can also play around with the start and with the end and what goes in here. So here's one more funky example. This one I'm starting at 3 and going to 7. And that the thing that I put in is xi equal to I squared. So what do I get? I'm starting here at 3. So I get 3 squared plus 4 squared plus 5 squared plus 7 squared, and so on down the line. So this is summation notation. All right, so now let's return to the original area problem that we've seen before. Our goal is to figure out what is the area underneath this curve x squared. And the technique that we had seen was that we were going to use an rectangle approximation. Here I've given the right rectangle approximation adding up all the way along, and we previously computed that the area, I sum up these different rectangles and I got this value 0.44. What I would like to do now is try to represent what's going on here using summation notation. And the way I'm going to do that is follows. Down at the bottom, we have these widths, 0.2 everywhere that we've written in our sum. That was going to represent the widths. And I'm going to put this together as the sum of 5 things. So I want a sum from 1 to 5. And so the way I write it is the sum from 1 to 5 of xi squared. That's like the 0.2 squared, the 0.4 squared, the 0.6 squared. So xi squared multiplied by these widths, the 0.2. In other words, this area is like the sum of the area of the rectangles, where each rectangle has a height, the xi squared, and has a width, the 0.2. So this really just means the sum of rectangles, the sums of the areas of rectangles that have a height and have a width. Now, what actually is the xi? In this case, the xi squared, if we look at what we've written out here, 0.2 squared, and that corresponded to, if I go down to 0.2 up here, the 0.2 by my function, which squares it, is going to go to 0.2 squared. So the x1 is going to be 0.2, the x2 is 0.4, all the way down to the x5 being 1.0. Those are my sort of 5 locations. If I wanted to write this a bit more generically, one thing that I could do is I could try to write out xi, and notice that they're all multiples of 0.2. 1 times 0.2, 2 times 0.2, 3 times 0.2, x4 is 4 times 0.2. So I can say that generally xi is 0.2 times whatever I is. x5, for example, is 5 times 0.2, which is 1. So what I have managed to do is my original just sort of summation we wrote down, I've given specific labels to what the x1, x2, x3, and generically xi is going to be. And so finally, taking this formula, this xi is 0.2i, and putting it into my area formula, I can clean this all up as saying the area is the sum from 1 to 5 of 0.2i squared times the final 0.2 times these widths. So I haven't really done anything conceptually different here. This is indeed going to be the same 0.44 that we computed in the previous video. What we've accomplished in this video is to find a notational efficiency to write down the sum of these areas. And it might not even seem that beneficial when our numbers are going only from 1 to 5, but if I was asking 1 to 1,000,000, it'd be a lot more beneficial if we could write it with summation notation than if we had to go and list all the different values. And indeed, this notation is going to be very important for us as we try to compute these values not as an approximation, but to figure out exactly what the area is. Because right now I'm only figuring out the area of the rectangles. And it's going to be in the limit as this 5 becomes really, really large that we're going to be interested in what the actual area is. So the various steps, if my goal is to figure out the area under the curve between 2 points A and B, are, first of all, I want to divide my interval into n subintervals of width dx. In the example that we've seen, we had a width of 1, and then we divided that into 5 different subintervals, each of width 0.2. So that's our first step, we divide it up. Then we're going to choose a point xi inside of each subinterval, and we've seen there's a couple possibilities. You could choose the left endpoint, you could choose the right endpoint. If you want to, you could choose the midpoint, you could choose the maximum value of the function, the minimum value of the function. There's actually quite a lot of different possibilities, but I usually just like to choose the right endpoint. But nonetheless, you just choose some point in each of these different intervals. And then we're going to form our rectangle approximation, and it's a sum. It's a sum of little rectangles. And those little rectangles have these widths dx, that's what we've already determined, and they have these heights, the function value at whatever points you've chosen. Usually the function value evaluated at, say, the right endpoint. So you get this formula for the rectangle approximation. And then what our goal is to take this formula for the rectangle approximation and take the limit of it as n goes to infinity. And so that's going to be my final step. My setting of my area is this limit as n goes to infinity of those rectangle approximations. Or in other words, limit as n goes to infinity of this formula we've seen, the sum of rectangles, height of f of xi, and width of delta x. Now, this concept, this idea of taking an area and writing it as a limit of a rectangle approximation is really, really important to the development of calculus. And it's so important that we're going to give it a fancy new set of symbols. So now I'm going to define for you a new collection of symbols referred to as the definite integral. I'm going to say that the so-called definite integral between the values a and b, notice that this is the curve between the 2 points a and b. So this is the integral from a up to b of my function. I write this weird little dx symbol, is just what I have here. The limit as n goes to infinity of the sum of these rectangles where they've got heights f of xi and widths delta x. And really what I'm doing is I'm defining this entire collection of symbols holistically. The dx here is related to the delta x, although we use a little bit of a different symbol. We think of delta x philosophically as a small but still non-zero interval, something like 0.2. We think of the dx as sort of infinitesimally small. There's a small change in the philosophy of this that we'll delve into more in the future. So we give a little bit of a change in variables, delta x versus dx. The function remains the same, and the other sort of oddity you might note is that for the definite integral, this symbol, I put the a and the b. But over here, I don't explicitly put the a and the b there, but it's there. When we take our interval and divide it up into the subintervals of width delta x, indeed the a and b is needed to determine where the xi's are, to determine the width of the delta x, and so forth. So the a's and b's are built into this formula, they're just not written down explicitly. The sort of big picture takeaways that you can think of an integral sign is an integral sign is basically just a sum. It's a sum, but a sum where you're not taking these really discrete separate points and adding up all these different rectangles. In the limit as n goes to infinity, they're getting smaller and smaller and smaller and smaller, and you're taking a sort of infinite sum. That's what this symbol denotes.